Welcome to Study Loop.
So here the final angular velocity would be 0 radians per second, and the initial angular velocity would be 317 radians per second. We can then say that here we're going to combine equation 1012 and equation 1045. At this point, we can say that the net torque would be equal to the moment of inertia times the angular acceleration. This would be equal to 2/5 mr squared multiplied by negative omega initial divided by t, and this would be equal to negative 2/5 times mr squared omega initial divided by t, and we can solve. So torque would be equal to negative 2/5 times the mass of 1.65 kilograms multiplied by 0.226 meters quantity squared multiplied by 317 radians per second, all divided by 15.5 seconds, and we are getting a torque of 0.689 Newton meters. This would be our net torque for part A. For part B, we can, from equation 1040, we can simply say that the force would be equal to the net torque divided by the radius. So this would be 0.689 Newton meters divided by 0.226 meters. This is giving us 3.05 newtons. We can then say that C, we're going to use the exact same expression found in part A, but now we have a radius of 0.854 meters. So the net torque would then be equal to negative 2/5 times 1.65 kilograms multiplied by 0.854 meters quantity squared multiplied by 317 radians per second, again all divided by 15.5 seconds, and this is equaling 9.84 Newton meters. And then for part D, we're using equation 1040 again. So part D would be that the force would be equal to the torque divided by the radius. In this case, it would be the torque that we found, 9.84 Newton meters, divided by our radius of 0.854 meters. This is giving us approximately 11.5 newtons. This would be our answer for part D. That is the end of the solution. Thank you for watching.